chapter 32 with 71 and 77, at least some of the stuff we can talk about regarding that. 71, from chapter 32, number 71. Two frictionless conducting rails separated by L equals 55.0 centimeters are connected through a 2 ohm resistor, and the circuit is completed by a bar that is free to slide on the rails. A uniform magnetic field of 5 Tesla directed out of the page permeates the region. What is the magnitude of the force Fp that must be applied so that the bar moves with a constant speed of 1.25 meters per second to the right? What is the rate at which energy is dissipated through the 2 ohm resistor in this circuit? So that's some neat questions. Neat questions that can be asked there, you guys. Let's see what we can say about it. Let me also go here. I got 71 written there, but let me also write it here and then kind of walk across. With 71, they are telling us there's a bar that's on frictionless rails. It completes the circuit. We have to pull this thing with a force Fp, for pulling, I guess. The B field is out, comes out of the board. So it's doing this. Et cetera, et cetera. So there's the B field coming out. There is a resistor. That's R. This length right here is L. And there's a width here, but the width varies because you're pulling this thing. So this thing's getting pulled. Why on earth did I try to do that? But I did. Okay, let me try to write it a little more neatly, I guess. There you go. A little bit easier. All right. So it's coming out of the B field's coming out of the board. We got this. We know that if we move this way, what's going on? If we move to the right, if we move to the right, we are increasing the flux through here. If that's the case, you've got to situate. Well, there's a lot of ways you can play this. A lot of ways you can play it. I told you it doesn't matter how the flux is changing. Nature doesn't know any better. As long as the mathematics holds, nature will behave as though you're dealing with a simple generator. That's how nature will behave. It doesn't really matter how the flux is changing, as long as it's changing in a way that is consistent with the prior mathematics. The prior mathematics will describe everything that's going on. Pretty fascinating stuff. There are charges in this bar. The charges are being moved that way. The B field is that way. Charges moving to the right, B field coming straight out at us. Let's do the right hand rule on this. Moving that way, B field that way, roll the fingers, bam. The current, the induced current is going to be this way. So this thing is going to go clockwise. It's going to go clockwise. Why is it going to go clockwise? Because when it goes this way, roll your fingers here. The B field goes into the board. You're increasing the B field by moving that way, so this B field that's induced will go into the board. It'll try to undo the increase in the B field. It'll try to undo the increase in the flux. Better way to put it. It'll try to undo the. So how do if I increase the flux coming out, how do I decrease the flux coming out? Have a current going this way, roll your fingers go into the board and oppose it. Another way you can view it, this is the crazy thing. View this as a positive charge right here, going that way. The B field comes out, do the right hand rule, moving that way, positive charge moving that way, B field coming out, roll your fingers into the B field. Wow, the current goes that way, it goes that way. It's still consistent. The mathematics is forever consistent. It's crazy. Nature behaves in a manner that's quite predictable oftentimes. Perhaps not always, but oftentimes. All right. So we're looking at how some of this stuff looks. Okay, so got this. So the current is going to go clockwise. The induced current will go clockwise. We'll figure out what that is and what's going on to actually have this happen. Okay, so let's take a look at it. Let's look at some of what we got associated with this. There is going to be a current. If there is this current, you guys, let me just think for a second here how we actually want to look at some of what's going on here. It's very crazy. You've got a current that's being induced going this way, straight down. You've got a B field coming out. So if the B field is coming out and the current's going this way, why don't you remember that's all a ripoff from this. And there's stuff we've done pertaining to that. One's born of the other, so to speak. This guy right here gets you out of the woods in a lot of things. This thing gives you an intuitive explanation of a lot of things, including Lenz's law. You can make Lenz's law happen using this. And then if it's in other circumstances where this is not obviously happening, we said that nature behaves as though this is happening. Even when it's not happening, if the change in flux is predictable in a particular way, is occurring in a particular way, nature doesn't care how it's happening. There are things that are it'll still solve the same way. It'll still give you the same induced electromotive force when we're doing stuff like this. So we got here, you can look at this. This guy gets us here. Let's look at it one more time. I goes this way. There's a lot going on here, actually. A lot going on here. We're looking at a situation where let's see exactly how we want to look at it. Just want to see exactly how I want to say it. This thing's somehow anchored on here. This guy's moving. Let's just look right here I don't want to complicate this more than we need to. B field comes out, current goes this way, IL is this way, B is that way. So what we got is you got the B field coming out, you got the I going that way, I cross B, do the cross, I cross B, bam, your thumb goes that way. There's a force pulling it that way. What does it mean? You better be strong enough to pull it out. There's a force drawing it that way, and that's kind of what's going on. So you look at it. See what we got. Number of ways to go here. And I've shown a lot here. I don't know if I'm going to do. Again, all of this is in the notes, you guys. I just gotta find the notes myself sometimes here. All right, here we go. So we said a lot of stuff. We wrote that over there. It is a constant speed that this is happening. So let's see what we can say. In terms of magnitude of what is going on here, what's the E field? Again, they're asking us, the question they're asking us, this is a new side of the question here, I guess you could say. You know, what is the magnitude of the force B that must be supplied so that the bar moves at a constant speed? Well, the force P and the B force, that F right there is the same as FP. This guy right here, associated with magnetic force, these guys are, in terms of magnitude, they are equal to one another. Why is that? Because it's being pulled at a constant speed. There's no acceleration taking place. So there's no unbalanced force on this in this process here. So observe, E equals N d phi b dt. So let's see what we got here. We're going to say that E equals, in terms of magnitude, let's not worry about the negative sign right now. We're already aware of what direction everybody's going in. So let's kind of deal with it. There is one turn in this thing. That's just one thing right there. And the B field is constant. So I just need to find dA dt. dA cosine omega t, whatever, all this stuff. Let me find dA dt. How's the area changing? The area is changing like this. That's rather significant. I hate to say it. A can be used a lot. A can be used as a constant. It can be used as a variable. Here it's going to be used as a variable. dA, if they're both variables, guys. If I want to do this, if B is a constant, I got that. How does the area change? The area is L times X. X is the X direction. Wait a minute. L is the straight up and down. That ain't changing. BL dx dt. Dx dt, that's another word for speed. So that's pretty important. That's where they're getting that from. That's where all that came from over there, you guys, that I had written. And what does that mean? Well, E is 1 times d phi b dt, which is all this. 1 times b L dx dt, which is BL V. V is the dx dt. How much current? They're asking how many, what does that imply? Well, it implies a lot of stuff. Current is this divided by R. They're all defined in terms, current, resistance, and electromotive force are all defined in terms of one another, you guys. So that's not a huge issue. So let's see what we got here. We got BL BLV over R. And, what's that going to be? Well, okay, I just figured out what I was. That is the induced current. That induced current makes it hard for you to pull it. It's a pretty profound conclusion. You ain't just pulling this thing and you're going to get away with it. If you're going to increase the flux that goes through there, if you're going to increase the flux that comes through, here, you've got to move something. Well, not only that, if you're going to increase the flux that comes through here, you are going to have to move something. To move something means you're moving charges, whether you know it or not. And there's going to be a force opposing what you're doing. That opposing force is associated with the actual current that's generated because of that motion. So there's a current generated, and that force will oppose the fact that you're trying to increase the flux. Beautiful. I mean, fascinating conclusion by itself in its own right. So what do we got here? Well, everybody's hitting at a 90-degree angle, you guys. Everybody's hitting at a 90-degree angle. This guy's coming out at 90 degrees. There's just 90 degrees angles everywhere. That's all right. The sine of 90 degrees is 1. So that ain't going to be a problem. That ain't going to be a problem at all. So what do we got here? It's going to be IL cross B vector. FB, in terms of magnitude, is going to be IL, small, big, doesn't really, that's not a big deal. ILB, sine 90 degrees, that's 1. Let me see a little bit more what I want to say. Yeah, that's fine. That's the force, and so let me see here what we're going to say. I mean, I think we're looking pretty good. Yeah, okay, not a problem. Now, let's put in what I is. Yeah, looks pretty good to me. I mean, so we actually run through this. We're going to get B squared L squared V over R is going to be equal to that force, which is going to be equal to this. How much you got to pull it? Yeah. Surprising, surprising, very, very surprising. Put in all the values that they gave you. When you do that, you guys, at the end of the day, that's just simply going to be this. And that's it. That's it. That's what we got here. Now, that's for A. For B, the power is a lot of things. It's I epsilon. It's power is IV. It's V squared over R. It's I squared R. It's all the above. We got enough. I mean, they told us enough. We got enough. The power is simply going to be I times E. So what do we got here? So we said that E right here, you guys. Let me just try to think here. We derived the E to be this. So we're going to go. Now I showed you one thing. Now I'm about to show you another. It's the same. Like we said, it doesn't really matter. Let's write it like this. Let's go E squared over R. That's the V squared over R that we've talked about in the past. Power is equal to. There's the E that I underlined over there. E is BLV. E squared is B squared L squared over V squared over R. BLV, the quantity BLV squared. V right here is a small v, not a big V. Okay, you gotta watch out for this. This is the big V of voltage. You should write, the better way to write it is delta V. I guess I'm a creature of habit. I don't do that. That's different than this. This is velocity, or magnitude of velocity. This is potential difference. Just watch out. E is BLV. E is BLV. Square both sides. B squared L squared V squared over R. So the end of all this, you got that. There it is. You just got that. Plug in all the appropriate values, you guys. You got 5.91 watts. Fascinating, fascinating conclusion. I mean, the way this stuff works is itself very fascinating. So that's 71. That's 71. Let's go to 77. So for 77, you guys, it's going to be very, very similar type question, but let's do it anyway. I think it's good to do. Again, very surprising conclusions, man. To do something like this, you are inducing an EMF. The induced EMF induces a current. That current itself opposes the fact that you're actually moving. That's kind of crazy in its own right. I mean, it's just, if you think about it, it's a fascinating Truly fascinating conclusion. I mean, we're assuming that the circuit over there is tied to one end, and so the only thing that's going to move in the circuit is because the resistor is tied up and you're not going to move it. It's something solid. Nobody's going to move, and you're just moving the thing on the rails. And again, the fact that you're inducing current in there, the current that is being induced opposes the fact. Let me just kind of look at it a little bit for 1 second, guys. It's a wonderful conclusion. It opposes the fact that you're actually inducing current. You are inducing current, but it's hard for you to induce the current because the current itself, when it gets in there, is going to, the magnetic force is such, it's not going to allow you to move that easily to induce that current. Fascinating stuff, really. For 77, a conducting rod is pulled with constant speed V on a smooth conducting rail as shown. Okay, it's almost the same kind of drawing. There's a resistor on this one though, guys. A constant magnetic field B is directed into the page. If the speed of the bar is doubled, by what factor does the rate of heat dissipation change? So it's a constant magnetic field directed into the page. It's pulled with constant speed V. If you double it to a new constant speed, you double the speed, what's going to happen? By what factor does heat dissipation change? It's really tempting to leave everything up here and see what we're going to do. That right there seems to be saying an awful lot, and that's probably going to be the way out of it. This guy right here, we did all the grunt work for it. Now they do something a little differently here to you, but it's not, let me leave some of that up there, if you don't mind. The way they got this thing drawn is and they got, the rail. And you got this, and it's, coming in. Et cetera. There's more over here. So you're not like, it's not like you're leaving one place and you're going to places where the B field's always going in. This guy's coming out. Did they actually say what direction it's going? I don't think, or did they? Yeah, they did. So it's going V. If you double it, at what rate is the heat dissipation going on? This is pretty fascinating stuff. Let's analyze it a little bit. Christian, you can see this okay? Do you want me to move anything, or we're okay? So we got this right here. It's moving this way. Coming out that way, let's do what we usually do. I told you guys, there's something moving here. Let's say there's a positive charge moving that way, and you got the B field going in. Positive moving in the way, B field, bam, you're inducing a current this way. The current getting induced this way, that's going in, IL cross B. Wow, it's going to pull against you. It's going to try to stop you. Yeah, it might try, so it's still trying to fight you. So what's going to happen? Man, a lot's going to happen. I hate to leave this. That's okay. This reality is bringing us to everything. Same stuff, different drawing than this. Okay, so don't stay with this anymore, but it's the same reality. What's going on here, guys? If the positive charge is going that way, and there's a B field that way, positive charge going that way, B field that way, bam. Go, QV cross B. Here you go. QV cross B, IL cross B. No, QV cross B is what I'm going to do. So going this way, QV cross B goes that way. This is going to go around. Goes around here. Now some people are thinking what's going on over here. What's going on over here is I cross B is this, I cross B is this is sandwiching that way. Here, this guy would actually try to get away. I mean, what happens is it goes in, I cross B, it's going to pull this guy this way, just like that guy's getting pulled this way. But this guy's tied up over here, so he ain't going to go anywhere. Just like that one over there, everything at the far left is tied up. Over there and here, they're tied up, so this can't go anywhere. Only this guy can move. This guy's tied up, so there would be something here of significance. Let's say that. But here we go. It goes here. I cross B. Bam. IL cross B. It's doing that. Yeah. It's got everything. It's got all the features that we know. That we know what's going on. We know this, and we know this. So it all works out. So it's I cross B, IL cross B. You got this. It's going to go that way. If you double the velocity, you guys, we were over here. We found the force to be this in 71. So what do you think happens in 77? If everybody's the same, let's look at 77 now. Let's just look at magnitudes. If B is the same, L is the same, R is the same, if B is doubled, the force is doubled, my friends. If the force is doubled, twice the amount of work gets done. Well, you gotta watch out for that one too. I mean, this is where it gets kind of interesting. The force is doubled. That to pull this thing, you gotta pull. They didn't ask us this, but hey, by the way, what if they did? How hard is it to pull it twice as fast as you were pulling it earlier? Right here is how hard it is to pull it twice as fast as you were pulling it earlier. This is how it was when it was V. If you put 2V on there, it's going to be double. It's going to be double. Double the force to pull it. Okay. Well, let's compare the two. Compare the two. This is, and again, let's keep it with 77, you guys. I'm sorry, I'm going to leave it up there, but there's enough there, and I think we can do it. There's the power associated with 2V, and there's the power associated with 1V. The power associated with 2V, you put a 2V right here. The power associated with 1V if you square the quantity 2V, you get 4V squared. If you square the quantity V, you got V squared. So how are we talking about this? So how we're talking about it is, at the end of the day, and I showed it a little differently in the notes, but that's whatever. Look at the notes; it's why they're there. Let's not do them verbatim all the time. We're kind of running out of time, guys. This is not easy for the man that's kind enough to be helping me out right here, Cristiano. I appreciate it, and it's not easy, so it's a circumstance. We got to get through this stuff relatively quickly when we do it. So we got 4/1. This PV, the P2V, is 4 times the PV. So I left it up there, but there was so much in common, you got to leave it up there, I think, So that gets us through it. That gets us through chapter 32, the way I wanted to do it, I guess, and that's all right. Okay, all's well that ends well. We have a lot of stuff up there. You guys are gonna get dizzy with the stuff we got up there, but we got it. So if that's okay, I'm going to erase the chapter 32 stuff completely, and then there are these chapters that I'm going to do all together and just like straight through. There's going to be a total of. I'm just looking at a couple things. I gotta bend somewhere on this stuff. I wish I had more time with you guys. I wish things are different. Let's all really hope for the best on this whole process. I'm sure we're going to be fine. I'm sure we're going to be fine. It's just going to take a little bit of time.